Okay, so we are interested in the mobility of dry geophysical flows, such as pyroclastic flows and rock avalanches. And as far as pyroclastic flows are concerned, of course, we refer to the dense underflow and not the turbulent cloud above that. We know that the prediction of this mobility is a challenging multivariate problem, and we address it by means of laboratory experiments and numerical simulations. I'm going to show you now first our main conclusions, and then I will explain to you how we got there. Okay, so these are the main conclusion. The first one is that the finer the grain size, the larger the mobility of the center of mass. And the second is that the larger the flow volume, the smaller the mobility of the center of mass. Okay, these are kind of fundamentals which we need to understand to be able to predict flow mobility. I think it's useful to show the conclusion at the beginning of the talk, so it's easier than to follow the talk. Okay, so we release granular material down a curved chute, both in the laboratory experiments and in numerical simulations where the apparatuses have the same shape and the same size. And the longitudinal shape of the chute is as the shape of the flank of a volcano, whose equation is known. And the cross-section is trapezoidal, as in nature, where we get this shape when we have a V-shaped topographic incision with sediment infilling in the center. In the laboratory, we use an high-speed video camera to study the flows. So in the laboratory experiments, we use only angular rock fragment whose grain size changes, and also the flow masses change. All the other variables have constant values, such as the angle internal friction, rock density, coefficient of restitution, roughness of the chute surface, and so on. Okay, these are the end-member flows we got in the laboratory experiments, and that's an example of a deposit. You see here that by changing grain size and flow volume, we do change the number of particles in the flow. And this, the number of particles in the flow is a key parameter which affect flow dynamics. You see, this is, for example, is the flow with the larger volume and the finer grain size, so that we get the larger number of particles. And this is the flow with smaller volume and coarser grain size, so that we get the smaller number of particles. So you see, these are truly flows which move down the chute. They are not, vertical collapses, which result mainly in internal deformation. The numerical simulation are 3D discrete element modeling, and we use 3 polyhedrons, a cube, half a cube, and a quarter of a cube. Each polyhedron has always the same proportion in all simulations. So you see that the granular mass accelerates down the flow, reaches a maximum speed, decelerates and stops. And particle speed decreases toward the subsurface, and the simulation are carried out by EDM software, which is by DEM solutions. Okay, we measure the mobility of the flow as displacement of the center of mass, and because it is the center of mass which is telling us which flow dissipates more energy and which flow dissipates less energy. So you see that mu A is an apparent coefficient of friction which is equal to the vertical drop of the center of mass divided by this horizontal displacement. And we know that mu A is a function of a plethora of parameters, but in our simulation and laboratory experiment, only grain size and flow volume change. Okay, the laboratory experiments show a linear relationship between mu A and beta is grain size multiplied by flow volume that is then normalized by the channel width. We know that mu A is a reciprocal of mobility, so that as grain size decreases, mobility increases, and as flow volume decreases, mobility increases. This is the mobility of the center of mass, right? This plot is showing us something important, which is this notion here that the mobility of the flow does not depend only on basal friction, but also on the features of the flow. And this is, of course, an important notion to predict flow mobility. The numerical simulation provide an independent confirmation of the linear relationship, And you see here that only the flows with 3 polyhedrons and the same larger initial compaction plot along the straight line. And initial means before release, when behind the gate. I'm talking about the granular mass before release behind the gate. If I decrease the initial compaction, the mobility decreases. Similarly, if I have a flow of only cubes, for example, has a smaller mobility than a flow with 3 polyhedrons and all the other features the same. Here there is another important point to make, that in this numerical simulation there is no either air or gas among the particles, so the grain size effect is not due to any motion of seepage, upward motion of the air, which can support part of the weight of the particles. Okay, this is just to show that, you know, even the small differences of Moe values can be significant. If you consider a drop of 1,000 meters in nature, 0.83 correspond to an horizontal displacement of 1,200 meters and 0.86 of 1,165 meters, which is difference 44 meters, which could be enough to miss a building, for example. But this is just an example, just to read the differences. Okay, to understand the effect of grain size, we need to look at particle agitation. And we measure it by means of this parameter, which is an average square deviation of particle transversal speed, which is then normalized. You see here that as grain size decreases, you see blue, green, red, so grain size decreases, agitation of the particles decreases, and mobility increases. So why this is so? Because as particle agitation decreases, also the energy dissipated by the flow per unit of travel distance decreases. Let's measure this energy dissipation in the numerical simulation. You see this is total energy loss per unit of mass. And this is just an example of a flow of 2 millimeter grain size flow, and which you see have dissipated more energy than a finer grain size flow to reach each position along the slope. So these differences are small because these are values per unit of mass, but they are significant. Okay, why we use a speed component in transversal direction? Okay, we can say to measure the particle agitation, because it's, the larger the particle agitation, the larger the kinetic energy spent in a transversal direction. And more in general, and this is another important notion, is that the less mobile flows are those that divert more energy toward a direction different from the downslope direction. So this diversion occurs through particle agitation. Okay, now we know why, for example, if we measure the speed of the flow in the same spot along the chute, we see that the finer grain size flow are faster. So why? Because they have dissipated less energy to reach that spot. Okay, let's have a look at the grain size effect on particle agitation. Essentially, as grain size increases, we get a larger agitation per unit of flow mass. And this is due to the fact that there's a smaller number of particles in the flow, because we are comparing flow with the same mass. So that if grain size increases, the number of the particle decreases. Sorry, if the grain size increases, the number of particles decreases. And the agitation increases because it's due to the interaction with the subsurface asperities, so that it propagates inward. So the fewer the particle, the larger the agitation per unit of mass. So, so then you see the number of particles in the flow is a key parameter which affects flow dynamics. And we can see this phenomenon here in this particle image velocimetry analysis of two laboratory flows. You see that the plug, which is the portion of the flow with smaller particle agitation, is visible only in the flow with finer grain size and not in the one with coarser grain size. Okay, let's measure particle agitation again in numerical simulation, always with the variance, this time with the variance of the transversal component of speed. And in this plot, grain sizes increases upward so that the number of particles decreases upward because the mass of the flow is always the same. And you see that particle agitation increases, as we said before. Here we see something else. We see also that the flow with only cubes have larger particle agitation than the flow with 3 particles types, and all the other features the same. So why this is so? The difference here is in the number of particles. So the flow with only cubes has a smaller number of particles, roughly 9,000, whereas the flow with 3 particle types and all the other features the same as 23,000 particles, roughly. So again, it's the number of particles that make a difference here. Let's measure the energy dissipation, for example, in the numerical simulation. Again, total energy loss per unit of mass. And you see the flow with only cubes has dissipated more energy than the flow with 3 polyhedrons, and all the other features the same to reach each position along the chute. And again, differences are small because these are values per unit of mass, but they are significant. Okay, let's compare particle agitation in a numerical simulation between flow with smaller initial compaction and larger initial compaction. Initial, as I said, means the compaction of the granular mass before release when behind the gate. And you see that the flow with a smaller initial compaction has much larger agitation than the flow with larger initial compaction. This is true at the beginning of the journey. At later stages, essentially, the difference decreases, and sometimes they're also reversed. But if we measure we go and compute the energy dissipation, again, numerical simulation, you see that the flow with smaller initial compaction has dissipated more energy than the flow with larger initial compaction to reach each position along the chute. Again, differences are small because they're values per unit of mass, but they are significant. So why we get this phenomenon here? Well, what we think is that larger initial compaction means larger compaction also when traveling. And so smaller particle agitation, and so smaller energy dissipation of the flow. Okay, let's have a look at the volume effect on the position of the center of mass. This is due to the fact that when the slope steepness changes, the front of this flow stops before the rear of the flow, which accumulates at the back. So we see this in this particle image velocimetry analysis of the laboratory flow, which is depositing. And you see that the deposit propagates backward. So the deposit propagates backward. And so if we have a change of slope steepness, it can be either gradual or abrupt. What's happening here is that the front of the flow is always on a less steep slope than the rear, so that it stops before the rear. And the rear accumulates backward. But the larger the flow volume, the larger the amount of granular material that accumulates at the back, so that the center of mass shifts backward a longer distance. And that explains why when we increase the volume of the flow, the center of mass becomes less mobile. For example, if we measure the speed of different portions of the flow in the same spot, but at different times, we see that the front is always faster than the rear. Why? Because when we measure the speed of the rear, the front is already on a less steep slope, so that is hindering the motion of the rear and decreasing its speed. So the numerical simulation is confirming that the deposit propagates backward and that the front acts as a barrier during the deposition. It's only considering the, as we know, considering the deposit distal hand, that the hour ratio H over L, which we called before mu A, and now we call R, decreases as the volume increases. So this is the famous plot, that everybody's talking about. We believe this is to be mainly due to the fact that the larger the flow volume, the larger the longitudinal spreading of the deposits. Of course, as you said before, there are many more effects here, including liquefaction and so on. Okay, let's have a look at the granular flows from underneath by means of a load cell. And this is these are load cell profiles, which, as you see, consist of signal peaks. And we check they are due to particle collisions, essentially. And they make sense because peak height and peak number are a function of grain size and flow volume. if we go in the field and we measure, for example, basal force at the base of a debris flow in the nature, as well, we see the signal consists of signal peaks, and they are almost certainly due to basal collisions as well. And you see, this is also, you see, interesting to see there is a the topographic incision as trapezoidal cross-section. Okay, let's measure again particle agitation, this time by means of this parameter, which is an average square deviation of the basal pressure, and which is then normalized. You see that agitation A, which was measured by means of the speed of the particles, and agitation D, which is measured by means of the basal pressure, are positively correlated as expected. And okay, so the laboratory experiment showed that the agitation is proportional to tau, which has grain size at the numerator. And so you see again that the coarser the grain size, the larger the agitation of the particles. This relationship is interesting because it links basal pressure, grain size, and flow volume. Okay, our flows are realistic because they show also a segregation of coarser particles toward the top of the flow and the front of the flow. This is a numerical simulation. It's the deposit. The red particles are the cubes, which are those with larger volumes, and then you see they segregate toward the top and toward the front. And as we know, this is a kind of segregation that are seen over and over again in natural geophysical flows. Now the question we can ask then is why there is a segregation when there is no density contrast between matrix and segregating particles. So we carried out an experiment in the laboratory and with rock particles on a rotating steel disk. And of course we get segregation toward the top sometimes. And this is due to the fact that segregation toward the top is due to the fact that particle agitation increases downward, so that there is always a force acting on the segregating cluster, which point upward. And if the weight of the segregating cluster allows it, the segregating cluster will segregate upward. And while there is a segregation toward the front, it's because the speed of the particles within the flow increase upward, so that whatever reaches the top will move faster toward the front of the flow where it will accumulate. You know, we know there are some semi-quantitative equation which describe segregation toward the top. Oh, sorry. Okay, so this is the conclusion we saw before. So we saw a grain size effect where the finer the grain size, the larger the mobility of the center of mass. And this is due to the fact that energy dissipation of the flow decreases. And it's interesting, again, that this is due to the fact that it's confirmed by numerical simulation when there is no air between the particles. So gas fluidization or self-fluidization is not possible. The volume effect is due to that the larger the flow volume, the smaller the mobility of the center of mass. And this is due to a sort of geometrical effect which occurs when there is a change of slope steepness, either gradual or abrupt. Is however not less important. Just a few concluding remarks. We can say that flow with different grain sizes are like cars with different fuel efficiency engines. So if we change the grain size of the flow, then we dissipate less energy per unit of travel distance. Particle agitation is a key in determining flow dynamics, and particle agitation is a function of the number of particles, which is another key parameter. Concerning the volume effect, so as I said, it's due to a change in slope steepness. This is not less important though, because we need it to trigger the position, and this is true in most of the cases, really. We believe our relationship to be scale invariant, and they are very basic effect of grain size and flow volume, and they are probably true in nature as well. And finally, the 3D discrete NI modeling predicts the relative mobility of granular flows. And this is true also without a prior adjustment of the parameter values to get the desired results. So that's it.
question?
Okay, I think in nature, because the problem is that what people do usually is to compute H over L considering the distal hand of the deposit. And the thing is that the deposit of a flow increases significantly, sorry, the spreading of the flow, the longitudinal spreading of the flow increases significantly as the volume increases. And so H over L decreases a lot. So these extremely low values are due to the fact that people take into consideration the distal hand of the deposit and not the center of mass. And of course, the distal hand of the deposit is important as well because we want to know how far the front goes because it's where it can do damage, so of course. But I don't think it's necessarily due to the fact that the flow with larger volume dissipate less energy. Of course, you know, as in the case we've seen before, if there is also liquefaction of the flow, then you increase further the mobility of the distal hand of the deposit. Sorry, I don't understand what you said. What did you say? Well, then is probably due to the fact that the flow are either gas fluidized or liquefied or something like that.